Good afternoon. Welcome to Krishna's class. Let us continue with our uh, process for constructing the Lebesgue measure on RQ. As pointed out earlier, my last lecture, we are going to exploit the power of the Rees representation theorem. And in this context, we have already explored how it works in a known circumstances, namely on RK, and we constructed the right kind of, or we have the right kind of linear function on CCR, which is positive, and the measure determined by that is essentially the Lebesgue measure. So that work we have already explored. Now we were exploring it from the point of view of trying to understand how this particular linear function can be obtained, so that we can generalize it into the case of RK. So I think we have been fairly successful in this task. So what are we looking for? We are looking for we have X as RK, etc. Then we have that this is locally compact, Hausdorff space. It is even sigma compact, which is also now we can use the power of the previous theorems that we have developed on this and apply Rees representation theorem to arrive at the Lebesgue measure. So the actual problem is finding out the right kind of linear function. Okay. So on R, that is k equal to 1, we know how to get hold of that. In fact, you see that lambda is a non-negative linear function defined from CCR to R, which is linear, positive, linear, positive. Then we have R, the Lebesgue measurable sets, and the Lebesgue measure such that where Now this is the relationship between R, M and mu. Now if R, and you see that this is the Riemann integral. Which exists. Why it exists? Because we are working on continuous functions with compact support on R. So all continuous functions with compact support are Riemann integrable, and therefore the Riemann integral is well defined. And if we choose this as then it's a Lebesgue measure. Measure space with mu as the Lebesgue measure. Okay, the problem when you work on RK is this. What is the Riemann integral of f on RK? So on RK, the problem is lambda f is chosen as integral over RK fx dx, where x belongs to RK. And this is what we expect. But the problem is then you have to completely build up and say what exactly we mean by Riemann integral. Now if we want to follow this track, then the problem is you have to define what the Riemann integral is on RK and then explore all its properties, etc., etc. It's a long-winded process. Riemann integration on RK, which is a laborious process. Okay, but explorations that we did. So our in this regard, is to exploit the power of the resurrection. In fact, we have seen the convergence of the classical Riemann integral leading to the Lebesgue measure, and also it leads to the linear functional on CCR in terms of the Riemann integral. Now, this is the one that we would be aiming at. But unless we develop the complete Riemann integral theory, integration on RK, you cannot write down this part. Okay? But what exactly is a linear function on CCRK? If you look at this, we are looking for a positive linear function. So we have to determine it's the right kind of positive functional and then apply the Rees theorem. So that's our task. Since we do not have the integral defined, we have to somehow arrive at this. So what did we do? Going back to R, we have seen that lambda on has the limit of a sequence of linear functions lambda n And a careful examination of this shows that precisely is precisely the and upper sums upper sums of f on okay. So you recall, let me just briefly recall this and make 2-3 statements about it and then see. Given f belongs to CCX, we have support of contained in some compact interval A. AB is a closed bounded interval. Now all continuous functions defined on closed bounded intervals are Riemann integrable. Okay. F is continuous on Riemann integrable on AB and hence on R, because see we are talking about functions okay. How do you get this Riemann integral? We define H to be okay. Let's start with the basics, the notations. Let be the set of points M 2 to the power minus n. Where m is a positive or negative integer, all integers. Okay. Then contained in sum m1 to the power minus n, where m1 it is in some AB and that AB can be considered. So the support of F is contained in this. Now you can define the following. So let the partition P let the partition P m1 2 to the power minus n, m2 2 to the power minus n be, that is say 2. So this be the partition. Okay. Now for this partition, we define the upper sum and the lower sum. Okay. So we define H to be sigma two to the power minus n, that is the length of the interval, times sigma f of characteristic function of are belonging to Z. Sorry, this is not. Two to the power n. Are belonging to Z. Which means on the interval, so this simply says the following. Suppose this is the interval R 2 to the power minus n and this is R plus 1 2 to the power minus n and f is such a function, then you see that this is going to be, the function is going to be defined as the minimum value of, this is f, this is the minimum value of f on this interval. So that is the infimum of f on this interval and multiplied by this. That means at every point on this particular interval, the function is defined by this. On a different interval, it is going to be different by this. And so, you see, based on this, the function gets defined properly. Similarly, sorry, I use g here. And hx I define 2 to the power minus n analogously. Sigma supremum of multiplied by chi of this is what we define. Then define G you define as sigma because this sum would essentially be a finite sum, so you don't worry about that. And similarly, you define a careful examination would tell you that this is nothing but the lower sum and lambda n h is the upper sum. Of that means we have if at all the integral exists, now this is something which we write for the moment, but this is actually the so-called integral, something that lies between. Okay, so we will have in fact this result. This is less than or equal to lambda n lambda n h. Okay, this is the lower sum and this is the upper sum associated with f, right? Now one can show that given epsilon there exists a n such that less than epsilon. So you can find an n such that this is true. And consequently, you also have, now this is for an arbitrary choice of epsilon. Consequently, exists as infinity. Similarly, limit and you have limit and this we call the Riemann integral of and we shall designate it by therefore that is lambda f, and this is essentially where this is the Riemann integral. Okay, and lambda is a linear function. Positive positive. What is the crucial thing? Crucial thing is to get a partition of the interval here. Okay. So we will examine this and how to proceed in the case of RK. We try to follow the same path. So how do we do this? Let us work on this. So we have to do a partition of R. So here we did a partition of R. So now we have to do it for RK. On RK, how do we define the partition? Okay. Now for that is the first job. For n equal to etc., let P and B be the that means it has components alpha 1, alpha 2, etc. alpha n. X is Rk whose coordinates are integral multiples of the power minus. That is the first thing. Therefore, what happens? So let us take R2. In R2, we take up points with coordinates are 2 to the power integer times 2 to the power minus. So you have get a rectangle box, and these points become points with multiples of 2 to the power minus. Okay, the coordinates are integral multiples of 2 to the power minus. Okay. For example, this is, we shall write this is 1 to the power minus then this is going to be, we are going to change this by 1. So this point has coordinates m1 plus 1 2 to the power minus n and m2. Okay, just draw this like this. For the case k equal to 2. This is what we are. This is the plane. Suppose this point has coordinates m1 2 to the power minus n, m2 2 to the power minus. Then this point has coordinates m1 plus 1 2 to the power minus n, m2 2 to the power minus. And this point has coordinates m1 2 to the power minus n, m2 plus 1 2 to the power minus n. And this point has coordinates this is what you call a sort of you can call it a 2 to the power minus n cell. Okay. And then what is happening is that the whole space is now divided into this, right? So that's understanding. This is a 2 to the power minus n box. Or what do you call a rectangle or a square. Okay. Similar comments do apply for the case k. So in the case of k equal to 3, it is going to be a cube. Okay. And then you get hypercube, etc. when you change the dimension of the space. So that's not difficult to understand. What is that? Let this means each edge and then of course the corners are of with the coordinates multiples of integral multiples of that's the meaning. Then this we have already seen. Which we have proved. So properties are, if n is fixed, each b, if this we have already examined, q prime is an element of omega n and q double prime is also an element of omega n, or empty. That is for a fixed n. This is exactly what we have said. Okay. Fine. This way. B, if or this property is there. Secondly, the third property is, if Q belongs to volume of and for exactly 2 to the power of minus n minus r k points this is another. The fourth property is, now this we have already examined. Every non-empty, this is important, open set is a countable union of disjoint boxes belonging to omega 1 union omega 2. This we have earlier worked out. Etc. etc. This we have already seen. Now what are we going to do next? Now we are in a position to state the theorem. So statement of the theorem. With these notations we can now state the theorem. This is the statement of the there exists a positive complete measure M defined on a sigma algebra script M in Rk properties. A measure of every Kcl. We have already defined what Kcl is. Script M contains all Borel sets. That means all open sets are there, closed sets are there, and then you have the arbitrary intersection of open sets. That is what you call F or G delta, and then arbitrary union of closed sets which you call F sigma. And then Once again, taking further arbitrary unions and arbitrary intersections and so on, so you get F sigma, delta F, sigma, sigma, delta F, sigma, delta, delta or F delta, sigma, etc., etc. So all sorts of combinations do come there. More precisely, if now we are exactly characterizing this sets, this implies if and only if there exists A and B in Rk such that E is squeezed between A and B. A belongs to G delta and measure of also so M is a regular measure, okay, and then every E is squeezed between an F sigma and a G delta, where G delta is the countable intersection of open sets. F sigma is countable union of closed sets. So you see that if this is E, E is squeezed between, this is an F sigma, this is a G. So these two sets. So this is an F sigma, this is an F sigma, and this is a G delta. That is the structure of the measurable sets. The third property is that M is translation unit. That is where scripture. That is the translation. And of course, X belonging to any element of D. If mu is any positive translation, translation invariant Borel measure on RK such that mu of K is finite for every compact K okay, such that the measure of E, mu of E is essentially a constant times the Lebesgue measure of that is the relation between any other measure having this translation invariant property or translation invariant property as well as defined on all Borel measures. Okay, or all Borel measure okay sets. Then this is going to be okay. That means in some sense this is unique. The measure that you define or that you obtain is unique except for a scaling factor. Okay, that is measure is unique. The scaling factor. E, if T is a linear transformation, RK is a linear transformation of RK, a real number it is associated T such that measure of T of E, the image of E under T is equal to delta T okay, for every this is another feature. In particular, if T is a rotation for all Borel sets. So this is the outcome of the theorem. Okay. Now I think this is a nice place to stop. Next time I will start with the definition of the lambda n and then systematically work through all this. Okay. Thank you very much. Most probably we'll take it up.